So this is the final meeting of the course in this semester. Let's continue our discussion on this optional part. It is about tunneling and its applications, inside which there is a little bit of nuclear physics here. So last time we introduced the idea that when we want to consider tunneling, we need to know how to describe something that is traveling. And we know how to write down a traveling waves. But coming with traveling waves, there is an issue about how to properly normalize those wave functions. I also introduced a few ways to normalize them. For example, you can use the Dirac delta function normalization, or you could use a box normalization, or even you can construct a wave packet in order to treat this incident particle as a wave packet. Anyway, there are ways to do it. We also introduced an equation, a formula that you already learned last semester in quantum mechanics 1 about the probability current density. So you plug whatever wave function you have, and then you can get the current, the probability current. If it is electron, you multiply by the charge minus E, that is the electron current density. So last time we list out this standard tunneling problem. So we have something incident here upon a barrier of height U. Usually for tunneling, we are concerned with the energy of the incident particle is less than the barrier height U. This is a special case in which the two sides of the barrier are of equal potential energy. It need not be the case, but this is kind of a standard first example. I believe you did that. I think you did it even in a fancier way. You have something called transfer matrix, etc. But here, just remind you of the simplest situation. So now you have this wave function in region 1. Last time, we already considered such a combination. It really means there is an incident part, there is a reflected part, because the probability current density for this part will be going to the right-hand side, and this part will be going to the left-hand side. So it's like refraction. In the region 3 here, we write down a transmitted wave, because this thing, if you immediately think about the current density, it is F squared multiplied by h bar k over m. And that's the plus h bar k over m. That is to say, it is going to the right. In the middle is a finite region. And with energy E less than the barrier height, you have exponentially dropping and exponentially growing wave. It doesn't matter you include this because it is legal. The whole range is finite. It grows, but it grows just into a finite value. Then the situation is something like this. Last time we mentioned that after you do it once, you don't need to do it again and again. When you see these waves, you know the current density has two parts, traveling to the right. That's why we call it incident. This traveling to the left, call it the refracted part. Although, at the outset, it seems that there are cross terms. And if you do the mathematics right, using the current density formula, those terms do not contribute. And then on the transmitter side, you have this current density. We end with this discussion last time. What do we want to get? There are two quantities in a tunneling problem that we are interested in. Actually, if you know one, if there's no loss in energy, you also know the other. They are the reflection coefficient, capital R. The definition is about the ratio of current density, probability current densities. So it is the reflected one. I put a magnitude here because if you take the current density, there's a minus sign. It is the reflected one. It is traveling to the left. But we are only care about the ratio, okay? So the incident part, because region 1 has the same potential energy, the prefactor, which is the velocity, turns out to be the same for the two parts of the wave function. Thereby, they cancel, and so all you need to do is b squared over a squared in order to get the reflection coefficient. The transmission coefficient, similarly, is defined as the ratio of the transmitted current density to the incident current density. I emphasize that this is the general definition. In many other problems, especially if you are doing semiconductor physics, there's a lot of tunneling problem that you can do because one can make sandwiches of different semiconductors and they are good tunneling structures. So in this case, fortunately or unfortunately, because both sides have the same potential energy function being 0 there, the prefactor turns out to be the same, and then they cancel again, and then you look for f over a square, then you will get the transmission coefficient. But I must warn you that that is not the general situation. The more general situation, if you have such a tunneling problem, notice that the potential energy in region 1 is now different from region 3. Thereby, if you use the proper definition, you will pick up h bar k region 3 over m divided by h bar k region 1 over m. H bar over m can be cancelled, but this wave vector cannot be cancelled because they are different due to the fact that the potential energies functions are different on the two sides of the barrier. So in this case, the transmission coefficient must be calculated this way. And this is the formal way. I'm sure that you have done this problem in term 1 in quantum mechanics 1. So the trick is just to match boundary conditions. So you have 5 coefficients, A, B, F, C, D, okay? But one of them can be taken as arbitrary one, and you also see we care about the ratio. So you take A and divide through everyone, you are left with 4. Now you have 2 boundaries here and there. Each boundary, there are 2 boundary conditions. Wave function being continuous and the slope of the wave function being continuous. Thereby, you do the accounting, you know, you have 4 equations, you have 4 ratios. It can be done, okay? So at the end, it's a determinant equals 0 problem. Well, 4 equations, 4 unknown, you write it into a matrix. You solve for the 4 unknowns, it is a determinant equals 0 problem. So therefore, you can solve it by hand. I think this problem can be done. And I only show you the result. So the transmission coefficient as a function of the energy is below the barrier is given by this ugly formula. And then if you write everything out, K is the wave vector in the 2 sides. So they are just 2m energy divided by h bar square root, okay? So, and then kappa is the propagation constant in the inside the barrier. So it is given by something like that, okay? So if you plug in the parameters of the problem, this expression becomes this formula. So this is the transmission coefficient. No approximation yet. We just solved the quantum mechanical problem. So now explicitly, you get the transmission coefficient as a function of several parameters of the problem. The energy of the incident wave, E, which now is assumed to be below the barrier, U, and the barrier is of width, L. So you see, all of this are there, okay? L, how long is the barrier? And then U minus E is the energy deficient. Is the how much energy is not there for the particle to climb over the barrier, right? So it measures how low the energy is, basically, from the top of the barrier, okay? And that is a useful parameter, because if energy approaches you, you expect the transmission to be higher. It is nearly at the top, so it's easier to get through. Okay, now you can also solve for the ratio F over A, which is the B over A, which is the reflection coefficient, and then you get another expression. You plug in all the parameters, you also get a corresponding formula with all the problem parameters in it. Independently, you can add these two things together and prove this to be equal to 1. If you are confident enough after solving it, then you can use R is 1 minus T to get this expression. Okay, now that is the case when you don't have absorption. If you have absorption, then T plus R is not 1. You have some energy lost. More important for our discussion is to get a good physical sense on the tunneling formula or the transmission coefficient formula. In the transmission coefficient formula, we have this funny thing there, okay? And this is exponential something, you know, exponential x minus exponential minus x divided by 2. Okay, so by definition, it's something like that. And now, what if we are considering the situation where the in energy deficiency, U minus E, is big, that is to say, the E is not that close to U, and that if you find something on the transmitter side that is really very quantum, right? In classical physics, you have a ball, there's a wall, the potential is that high. When it encounters the wall, 100% it will bounce back. So if we consider that, we can also consider a rather thick barrier. So all in all, we would like to consider kappa L being much greater than 1. So in this case, we can ignore this term, okay? And therefore, we only include that, but it is in the denominator. So it is in the denominator. Therefore, you flip it up there. That is the most important physical sense of tunneling formula that, well, if you are going into applied science and engineering type of problem, this is the most important feature. So the feature is, it is exponentially sensitive to several things. By that I mean, you see, it is exponentially minus something. So it's dropping with the increase of this parameter up there. And what are they? If the energy deficiency increased by a little bit, that is to say, this is the barrier. Energy E incident here, okay? So this is the deficiency. You start from here, you lower energy a little bit, the deficiency become bigger. This exponential minus that quantity will drop by several orders of magnitude easily, okay? Exponential is very sensitive to the value in the exponent. Secondly, if the barrier width increases by 5%, say, okay? Again, it is exponentially sensitive and that will drop by a lot, okay? So when you see this, have this idea in mind. You don't need to do the mathematics every time, but you need to have some sense when you read a formula. These 2 points turns out to be very important in understanding alpha decay, inventing something called the scanning tunneling microscope, etc. So engineers are very clever. They may not know how to derive it up to a factor of 2, things like that, but they know the point. And I want you to know the point as well, okay? So this is what I just discussed. This is the energy deficiency, okay? If it increased by a little bit, the transmission drops. If it decreases a little bit closer to the top, the transmission increases by a lot, okay? Maybe 10 times, 100 times, things like that, okay? Secondly, if this barrier width increased by a little bit, transmission drops sensitively. If it is narrower, transmission increases sensitively. Get that? So now let's draw it out. What I mean is that I can draw this, or even I can draw this one exact formula out, okay? What am I drawing? The formula was derived for energy below the barrier. Therefore, the x-axis incident energy divided by the barrier height, I'm using that formula and restricting the range from 0 to 1. Energy is below the barrier, all right? Then I can plug the formula in and then draw a line, okay? So quantum mechanically, we see something like, it is very small actually for any reasonable parameter. For this example, you plug a combination of variables to be a number, and then you can plot it out, mathematical, whatever, okay? So it is small, but it is not 0, right? In contrast, classical mechanics, a ball hitting a wall that it cannot go through, then it is 100% rebound. So transmission is 0, okay? So this is classical mechanics, this is quantum mechanics. But I'm not trying to exaggerate the transmission coefficient. It is not big, it's tiny, okay? But the point is that it is tiny, but it's not 0. So this tunneling, if you see through the mathematics and the derivation, it is a wave, it is exhibiting the wave nature as that is an important point in quantum mechanics, right? You have wave functions representing the system, okay? So it is again a consequence of the wave nature of the field. Now we ask the second question. are there any tunneling effect for energy, incident energy above the barrier? This range, okay? We haven't done that. You have to do it again. By that I mean, you go back to this setup page. Now, the incident E is above the barrier. Therefore, I think what you need to do is to change the wave in the middle region, right? Into E minus I kappa X and E plus I kappa X. With kappa being E minus U, because E is now higher than U, okay? Then you match boundary condition, certainly the same mathematics difficulty, you can derive the formula. So you can do that again, or there's a lazy way. If you see through the mathematics, you compare this new form with our old form, then you see, if I pretend my kappa is the new ik prime, where k prime is this, okay? Then all the formulas should follow because they are the same mathematical form, okay? So either way, you get the same answer, of course. After you get the same answer, then it is interesting to plot the whole transmission curve out. In the last figure, we are only showing this part. This is E below the barrier. Now, after you do the problem again for E greater than U, so you have the result here, right? Okay, and here the curve is the whole line. This is the transmission as a function of energy. Now, interestingly, there are quantum mechanical effects even for the incident energy above the barrier. It is shown as a few of these resonances here. Okay, so for example, for this particular energy, it is above U, above the barrier. Nonetheless, the transmission is slightly less than 1. Okay, it's not much, it's 0.9 something, but it is not 1. So you see this wiggling a little bit, but when the energy becomes very high compared with the barrier height, then it approaches 100% transmission. Comparing it to the classical mechanics case, we know that below the barrier, 100% rebounding, above the barrier, 100% getting through. Okay, so this is the step function for classical mechanics. And then we have this, both a little bit of transmission below the barrier. This is called quantum tunneling, but I prefer just tunneling because classical tunneling, we see it in optics, okay? So, and there are wave effect also above the barrier height. All in all, this is a consequence, again, about matter waves. We are using waves to describe the physical systems in quantum mechanics. I just want to remind you that there's nothing really surprising. I look into Griffin's electrodynamics, trapped a line, and then I found the following problem. It is a problem about a fish, okay? And someone wants to see the fish. So this is air, ocean park, okay? So this is glass. So what I mean is this is epsilon 3 epsilon 2, dielectric constant or refractive index, and this is epsilon 3, okay? So you have region 1, region 2, region 3. The analogy here is this, right? The 3 regions have 3 different refractive index. That is the classical EM waves problem. And in our quantum mechanics problem, the 3 regions have 3 different potential energy value. And the case for EM wave is that EM waves can travel through, so you can calculate the transmission coefficient. You have the Maxwell equation governing the propagation. You write down the solution of the propagation of the EM wave, match boundary condition. The boundary condition has to do with tangential E field being continuous, and then the normal component of the D field, is it continuous? I think so, yeah. Okay, and then you have the same number of conditions, you match boundary condition, you can solve for the transmission coefficient, okay? So in this Griffin's textbook problem, students are asked to prove 1/t is given by this thing, okay? So therefore, t is given by 1 this thing, all right? Basically, if you do this problem for G greater than U, you will get the same answer. So it is just a wave phenomena after all. So with this, there are a few interesting exercises. One is a step function. It is also called a scattering problem. I look at your notes last term. You have done this step potential, either reflected or fully transmitted problem. And then, more interestingly, for application purposes, this is a double barrier situation where there is something called resonance tunneling. So you can imagine you write down an incident, reflected, and then you have 2 coefficients growing, decaying, and then you will have going there, here, and then growing, decaying, and then the transmitter. Okay, so how many coefficients you have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 coefficients. But one of them can be taken to divide through, therefore 8 remaining, okay? And now you have 1 interface, 2 interface, 3 and 4 interfaces, okay? Or 4 boundaries. Each boundary, wave function continuous, slope continuous, 2 conditions. You have 8 conditions to solve for the 8 ratio of the coefficients. Of course, that can be done, all right? Therefore, you can calculate the transmission coefficient versus the incident energy. This is the barrier height. Interestingly, for this problem, you will find, this is 1. You will find at some particular energy below the barrier, there is a 100% transmission. Okay? If you haven't done such a problem, I encourage you to try it out. It is a very interesting thing. And this particular phenomena is called resonance tunneling. Again, I must emphasize that that happens for a particular energy E that is below the barrier. So at this particular energy, there is a high chance of tunneling through this structure. Engineers are fascinated by this particular peak, and then there may be a lot of switching application. When you have a peak, it is a very good situation for when you go across the peak, suddenly something being switched on or off. Okay, when you go away from the peak, it's off. So once you have on-off, engineers are very happy. Okay, you can also go on to do many barriers, and this many barrier situation is related to solids and also something called semiconductor superlattices. By that, nowadays it's routinely that one can do a structure like 5 atomic layers of semiconductor A, for example, gallium arsenide, and then maybe 4 layers of another semiconductor B, perhaps aluminum, gallium arsenide, and then repeat gallium arsenide, aluminum gallium arsenide, and so on. This is called superlattices. In Chinese, it's called 丘真噶. Okay, and it is like a man-made periodic structure. All right, because nature in crystals give us nature-produced periodic structure, but in superlattices, it is a man-made periodic structure. We can control the width of the layer and so on. It is also related to tunneling. Okay. Now, before we move back to the discussion of alpha particle decays, so let me summarize the finding. For a single barrier, this is the key factor. Okay, although there are prefactors, but this is the most sensitive thing to the parameters of the problem. But last time when I motivate the alpha particle problem, the barrier is not a square barrier. So it's something like what I draw here. So how can we do it? Then you need to redo the problem. A trick is not to do it and guess what it is, right? But formally, you can cut the ugly shape into many rectangular one, and then using the rectangular answer and then put them together. Okay, exponential multiplied together is still a bigger exponential, right? Of course, you have learned in the previous course that there is something called the transfer matrix method. So that is the very basic idea about tunneling. And now I would like to go back to alpha particle decay. So it was Gamow, a very famous, a very interesting person in physics, who suggested or proposed that alpha particle decay, the mechanism of which is really due to tunneling. So in his picture, he has this idea in mind. So in a big nucleus, there are many nucleons. Occasionally, 2 proton, 2 neutron together. Well, you can think about this as a pretty big binding energy. It is a stable entity. So they try to move to the surface and then try to get out. Okay. So last time we already discussed that when the alpha particle gets out, then it is positive, they will repel each other. That is a Coulomb repulsion, okay? So as a function of the distance, the Coulomb repulsion will give you a barrier. I used the same page last time. So therefore, the alpha particle, before it comes out, is trapped inside the nucleus. This is the radial direction, so it stopped at 0. So you can think about there's another side here. It is also trying to get out in the other side. And from experimental data, we know that the alpha particle that comes out has the energy of 5 MeV, 6 MeV, that number, okay, up to maybe 10 MeV. But the range is not big. So it's a few MeV. So the situation is that the alpha particle is trapped inside the nucleus. It does not have sufficient energy to surmount, go over the barrier. Nonetheless, occasionally, it comes out, okay? And the barrier width is about the radius of a big nuclei, is about 10 to the minus 15, 10 to the minus 14 meter. That's about the right size, okay? So the idea now is to apply tunneling to explain some phenomena of alpha particle decay. So this is the cartoon picture. So the left-hand side is what I just discussed. Alpha particle trapped. Energy is about this energy when it comes out. It may be a few MeV less in energy to go above the barrier, okay? And then you can do a tunneling calculation. So you have a wave function here. You write down some wave function in the middle. The wave function, the particle comes out. You have this traveling wave going out to the right. You match boundary condition, then you can get a transmission coefficient. So in reality, we are encountering a more like a triangular barrier than a flat rectangular barrier, okay? So in rectangular barrier, that is the one that we discussed, we have such an expression for the tunneling coefficient. For this one, of course, you can do it again or cut it into stripes. So this looks like a small rectangle. So you can apply this, and then the next bit, you can do this and so on, okay? So it is not difficult to imagine if you have such a situation at the end, what you need for this factor is to turn it into an integral. For the reason, because the energy deficiency is now changing with this distance inside the barrier, okay? So it makes sense to turn this into an integral, and then now we have the energy deficiency being a function of x. And that is the most important idea here, because you see that if the energy E is far from the top, it has to go through a bigger range. So effectively, the barrier width is longer, okay? If the energy increases, say up to here, the deficiency is smaller. Accompanying with that is that the barrier width becomes shorter. Therefore, you would expect if the energy increased from here to there, both factors in the formula will help the transmission coefficient to be increased by many, many factors, okay? 100 times 1,000 times, 10,000 times. For the reason, shorter barrier width and smaller energy deficiency. Okay, so this is energy deficiency, and then you have to integrate from the starting point to the corresponding width of the barrier. Okay, so both factors will help to increase the transmission coefficient by many orders of magnitudes. Okay, so now let me give you some ballpark range. For a nucleus with 90 protons and maybe 120 neutrons, then it is found that the alpha particle comes out at 6 MeV. Well, very typical. Last time I showed you a list of number. And we can estimate how big such a nucleus is because there's a formula saying the radius goes like the mass numbers to the 1/3 power. I'm sure that you have seen this in Dr. Lin's course. I have the class notes from him. Okay. Nonetheless, you plug all the things in. The typical number for the transmission coefficient turns out to be 10 to the minus 30 or so. So it's tiny, tiny, tiny. So what does it mean by that? The interpretation of this transmission coefficient is, it is the probability if the alpha particle make one attempt in tunneling through the barrier, okay? Then in one attempt, the probability is 10 to the minus 29. Then you may wonder, how come we can still see alpha particle decays? Then it is a very educational point. For each attempt, if the probability is that tiny, the strategy is to keep on trying. Okay, in Chinese is 钱有功係嘛，勤有功係嘛? Okay, so every attempt very difficult to get out. Keep on trying. Okay, so we can estimate how many times it will try per second, for example. Okay, so this alpha particle inside the nucleus, okay, they have energy MeV scale. So they say taking it as kinetic energy, they are moving rather quickly inside the nucleus. So the radius is about 10 to the minus 14 meter. Okay, so they will make an attempt at the surface very frequently. This one not successful, go to the other side, try it and try it again. Okay, so in this estimation, just a very rough estimation, we see that an alpha particle may be trying, well, depending on the energy, 10 to the 20 times per second. And then for each time, each attempt, it can come out with a probability 10 to the minus 9. So then you will see that maybe per second, there's still a little bit of a chance, okay? And therefore, we do see alpha particle decay. And related to this, again, this idea also explains this phenomena that I show you in the motivation. Although the energy of the alpha particle that comes out from decays all fall in a very small range, a few MeV. Apparently, they don't look very different, but as we said, higher energy, the height, I mean the energy deficiency to the height is smaller, and the barrier width to conquer is smaller. That will make the transmission coefficient a lot bigger, maybe go from 10 to the minus 29 to 10 to the minus 23. When, well, off by 6 order of magnitudes or so, and then that will affect the lifetime by a large factor. Therefore, we see the lifetime span over many, many orders of magnitude, despite the fact that the energy of the alpha particle that comes out do not vary by much. So that is consistent with the tunneling picture. So that is the alpha particle story. The second application I would like to point out, due to the tunneling effect, is a very clever invention, and the importance of which is that once it was invented, then we have this new field of nanoscience and nanotechnology. So it is that important. It was the time I was a PhD student, so that is hot news at that time. So 1982, I think they are in IBM or something, some industrial lab. So they invented a not very expensive apparatus. It is called STM, Scanning Tunneling Microscope. So this is a tabletop thing, very small, okay? Not very tiny, but just something like that, okay? So the idea is as follows. You try to control a tube, just like a pen. So you have this tube. Of course, if you do it very nicely, the tube, the end of the tube should be a single atom, right? So more atom there, small, fewer. At the end, you have a single atom, okay? Now the idea of the scanning tunneling microscope is as follows. So let's say you have a metal conducting thing, okay? So you know they are made of atoms. So you use the pen, the tube may be a single atom. You try to put it very close. How close? A few angstrom down to that precision, okay? So that electrons can tunnel through air, the gap, air gap, from the, either from the pen to the material or from the material to the pen, okay? So what is the idea? The idea is to map out the morphology in a surface. Okay, now this is macroscopic, this is microscopic. Do you see me? Okay, now you see that in this particular surface, there are some atoms going up here and something that is lower a little bit and then go up a little bit and so on, right? Now, if you know tunneling formula, then you know the following. If I scan my pen, the tube of the pen, just horizontally, okay? Now at this point, the tube here is farther away from the atom below, right? So if there is a tunneling current, the current will be very tiny because it's far away. If I move to here, okay, then my tube, maybe I use a different color, okay, my tube is closer to the atom on the top of the surface atom here, and the tunneling current will be big, okay? So let me summarize. If I just move this pin, it is called the STM tip, horizontally, the current will fluctuate a lot. When the top atom is farther away, the current is tiny, closer. In the other atom, it will suddenly shoot up, okay? So do you follow me up to here? Now, these experimentalists are so clever. Well, or technically they are so good. Now, they have this idea. How about this? I want the tunneling current to be a constant. Okay, so therefore, they want their signal in their apparatus. The data that they take is a constant current. So they have to move the pin, the tube, at a constant height to the atom. So when the atom in the surface go a little bit higher, they have to do some mechanical feedback loop, a lot of electronics there. When the current start to drop, put it lower. When the current start to increase, make it higher, okay? So if you can control the current to be a constant, then when you move the tip, like this, let me do it again. So I'm trying to keep the distance from the atom on the surface a constant, okay? So if I record the motion, the movement of the tip, it is as if I am drawing out the surface morphology. Do you understand? Okay? Now, all in all, this is just tunneling, but in a very clever application, very clever invention. Okay? So, what can we see? I just discussed these two cases in particular. The usual way to do it is the constant current mode. For that to happen, we need a very sensitive feedback mechanism to move the tube up and down so as to keep the signal, the tunneling current that we measure, a constant value. And then recording the motion of the tip. It is like drawing out across one line the atoms on the top of the surface, on the surface of that crystal. Then you move the tube a little bit and draw another horizontal line again, and then by putting them together, now this may be the very first picture of an atom. Okay, now atoms were discussed by the ancient Greeks, I think 2,500 years ago about, okay? But they just sit down and discuss it in a philosophical way. Only in the 1980s, when we have such an apparatus, at least roughly, we are taking pictures of the top of an atom. And I think that is another big moment in science, right? Now it is no longer a debate about whether atom exists or it's just a convenient notion for us to understand different things, okay? Now it is really a picture of the head of an atom, okay? So it's a very clever invention, and then they got the Nobel Prize in only a few years. They got this thing out, 82, then everybody knows it is a big thing, and then everybody realizes it's not very expensive, and there are undergraduate projects, there are papers reporting that students can construct such an apparatus by themselves. Of course, it will not be in low temperature, it will not be very sensitive, okay, but one can still make it. Then some accidental discovery follows. So people are using this STM tube on the surface to measure the morphology of surface, but somehow they don't control it that nicely, and then they start touching the surface. Then suddenly they found that if there are some loose atoms on the surface, there is an effect, and not fully understood the mathematics, the formula, etc., but it works, is that this tube can be used to pick up an atom that is disposed on the surface and then transfer it and put it down to another place. So here is a very famous experiment. There are 35 xenon atoms put on a surface, and then the experimentalists used the tube of the STM to put them or transfer them one by one and put them into IBM. Of course, you know who did this experiment, huh? IBM lab, okay? So this is the very famous picture of writing. So here is really the beginning of nanoscience and nanotechnology. Now you can manipulate atoms. Of course, one can write Chinese, and also the Japanese can also write Yunji. They also use the same word. So I don't know whether this is written by the Japanese scientists or Chinese scientists. Okay, so I think let's take a short break, and then I will finish up the rest of this discussion on tunneling and its applications.